welcome everybody. So this is going to be the talk about tech art or tech art journey, or pretty much how we found multiple different problems, how we identified them, solved them, and had a little bit of fun through the process. I actually have my pointer here. Okay, so first of all, oi, tudo bem? For those that do not know me, I am Victor Nascimento. I am the current tech art lead at SMG Studio. And before that, I used to be a lead gameplay programmer, working virtual reality, doing open world, did that for a couple of years. And even before that, a whole lifetime away, in the distant lands of Brazil, I used to be a data scientist working with consumer goods. So that does mean I have a slightly uncanny knowledge about diapers, feminine hygiene, shampoos, so ask questions. And even before that, I'm a naval engineer. So I do have a bachelor. It's actually specialization in portuary operations. So it's less about ships. If you see a ship and it has my name, do not board it. You will die. It will sink. But despite looking like a mishmash of things, everything has a connection, that is maths. I really like maths. I talk about maths to everybody, so anybody that works with me, they love hearing about different quaternions or Euler or algorithms. I quite like them. Other things I do like is coffee and cake. So if you want to find me, I am the coffee cart. So it's quite on brand that I'm right in front of it. But to not say I'm an easy person, I am a Soulsborne Kiro Ring fan. So I play all of them. I didn't find a place to put Armored Core, but should be there as well. And what will happen here, right? So this is me. Right now, I'm going to talk a lot. I have a lot of content. I will try to go fast. I do want you guys to have time for questions. And to make matters worse, this will get a bit technical. I will be talking about binary, compression, optimization. But as a silver lining, the entire deck will be available online. I know the GCAP will upload the presentation itself, but at the end, there will be a link that you guys can download the slides right after this. So I do also have provide the slide notes, which have some documentation links, some of my thoughts, and I don't know, you might find some of them a little bit silly, but sure. With all that said, keep your hands to yourselves, and we're going to take this show on the road, and going to start with what is the project, right? So as I said, I work at SMG, and the project that this presentation is about was the biggest project that SMG has ever worked on. It is a multi-platform game, a party one that is super nice, but is confidential still. So what that means is that I did have to change some of the wordings, some of the expressions, so you guys cannot quite identify what exactly is the IP that we're working with, but you guys can understand the technology that we'll be talking about. And what is this technology, right? Majority of projects, it's more traditional in games that you have a 3D artist team that actually hand model assets and that get implemented and use an engine at runtime. But in our case, what we did was we still have the 3D artist, but what they build up is actually a library of small assets. So we're going to name them atomic meshes. These assets can be any small thing. So it could be a door, could be a window frame, a piece of a wall. And then we have a designer that jam all of them together and make a bigger model. So this is the asset that will actually be seen in engine. This is mostly set up in 4 different steps that are, first, the atomic mesh assets. Them themselves are the 3D assets and a scriptable object that has all the definition about it, followed by the build instructions that our designers build. So for this, they have a custom software that I cannot go into details that export a human-readable file with a custom file extension that I also cannot talk about. But we do read it in Unity using a Unity scripted importer. For those that are not aware, that is a Unity API that allows us to interpret the file in whatever way we want. Again, documentation is on the slide notes, so please stick around, like and subscribe. With the scripted importer, we actually managed to set up all the asset importing pipeline with data that is stored into the meta file. And lastly, but not least, we have the in-engine mesh asset. So at the end of this, what we end up having is an asset that is in the project that you can see just like any model and behave like a prefab. So you can just drag and drop into the scene and you can see pretty much the whole hierarchy, game objects, and the models themselves. All of this can be organized into this nice line. This pipeline does serve its purposes. So it allows us to actually use a considerably smaller 3D artist team to populate a much larger world, which can be used, can also be used in a few different projects. So open worlds or anything that it has a larger scale could be used. And it also provides a few other benefits. One of them is that because we started with, we tried to be very fast in the beginning, generated a lot of that library, not all of them were up to quality. So when we get later down the line, we started optimizing each individual part of them. We could easily feed the entire pipeline and update the models. Also, it allows us to iterate on the final design. So at the end, when we have the level, sometimes we realize that for game design reasons, we need some area to be larger, or for an animation to come through, we needed to maybe show something else or expand it. So all of these also feed back to the pipeline. And this and we follow this together, we have our lovely atomic mesh asset pipeline. And this is our AMP 2.0. And if you see 2.0, what does that mean? That there was a 1.0. But that came before my time. I joined the project pretty much at the end. And in reality, even 2.0, I already came in when it was already established. So I stepped into the shoulders of giants that set all the groundwork before me. But at the end of the time, it is great, okay? This pipeline generated very nice assets. It created a lot of good stuff. But the question is, does it actually work? Because at the end, as you can all imagine, jamming a lot of assets together generate very large meshes. That is not the biggest mesh we have in our project, but it's a very damn big one. 6.5 million verts, and that is not even a whole level. That is less than 20% of a given level. So in that, if you look there, I do say that it's 600 megs. Guys, the switch cannot load that. The switch cries and burns. So how can we actually tackle this thing, right? One of the first features we do have is visibility culling. This is very common in 3D modeling software, so you already can do that in Blender or Maya. But because our pipeline is always implemented in Unity, we had to implement one ourselves, which does have a few steps. First one, on the feature, when we are setting up the importer itself, we actually organize the, different camera positions. We can change all the FOVs, the distances. We do store their positions, position rotations. We also store occluders, which are effectively just Unity cubes. We do scale them up. This allows us to actually organize that if an asset will only be ever seen from a given camera angle, we do not need any of the vertices or triangles from behind. It also allows for intra-object occlusions. So if you have multiple meshes that have internal geometry, all that can get occluded. But from those, we do render for each one of those camera views. We render the model, but through a special R32 UWint render texture, which actually allows us to render not color, but data. That is just a visualization that I hacked so that it could be more interesting. Otherwise, it would just be red. And what we do there is we just grab all the triangles, we build a compute buffer out of them, and we just render their indexes, followed by grabbing a compute shader that will read each one of those textures and populate another compute buffer with a triangle if it is visible or not. So as we're reading, if we see triangle 32, we just go onto array and put 33 in reality. We just need to offset by 0, like offset out of 0. And at the end, we collect it all, just run for each one of those camera angles. Because we are just populating a buffer from 0 to 1, we are not actually incrementing that. We do not have issues with concurrency, and we can benefit from the parallelization of the GPU. At the end, we just get this data from the GPU into the CPU, define all the triangles that are not visible, that have not been populated, discard them all, do a very similar process to actually extract all the vertices that then become not used. We just run another compute shader that go through and just populate a buffer with vertices that are used by triangles. And then at the end, we clean everything. I do have code. I doubt anybody here is going to be able to read it. It is small, I know, but it's on the slides. Everybody will be able to download this. And I do have here I do have a pointer. I do have the main method or how things get called. I do have some of the shaders, exactly how things can be evaluated, and the compute in the end. But let's go to the nice stuff, results, okay? How much of an impact does this have? This is the same mesh that I showed before, and this is the mesh after the cleanup. Yes, that is a 90% reduction. We went from 6.5 million to 452,000 verts, right? So from 600 megs to down to 51 megs. The switch can finally start breathing better. It's still not quite there. It's still going to have some hitches, but we're going to improve it. A next step we do have is, this is a very specific domain knowledge. When looking at our atomic meshes, we realize that a lot of them have some very small details. So it could be an emblem that is on the mesh, and they have a few different types, but it does happen a lot, and they either end up eating a lot of geometry, especially affecting our light maps, because they end up eating a lot of the resolution available on those light maps, although they don't have much fun impact, not on the light map calculation or shadow casting. So we did decide to make a different feature for it, where we're gonna draw them instancing. So we're gonna have our detail drawer. Detail, as you can tell, it's a little bit hard for me to keep saying, so we're gonna give a different name. They're blink. Okay, they're a little bit useless, but they look damn nice. So what is the blink drawer, right? How does it actually fit into the pipeline? First, we define for each one of those atomic meshes, we have them split. So we have the base mesh and we have the blink definitions. So for those blinks, we do have their position, rotation, scale. We do have the exact type of them. And on the feature setup, we can enable or disable the blink drawing. Being enabled, we do expand alongside the meshes themselves. We do have a scriptable object that is a blink collection. There are some reasons why we don't want to enable for everything. I will get to that a little bit later, so put a dial on that. What is the blink collection, right? I said it's a scriptable object. Seems simple, but what exactly is it, right? First part, it has the bounds, so we just go through every single one of those blink definitions and grab their bounds. This will be used for visibility evaluation later. Then we have a blink type collection array. So these arrays made of just C# objects that get serialized. Each one has the blink type, because we do have a few different types. I think we have roughly 8 different types. And for each one of them, we have a blink element array that in turn is another C# class that has a TRS containing the information about where to place them, the material that is packed into a single UInt that we will decompress on the GPU when we get to render everything, and the light map UV plus scale. The reason for that is, as I said, although they don't have an impact on the light map evaluation, they do need to sample from it. So the strategy that we use is we have the base mesh and we evaluate the position of the blink itself and get the light map UV of that position. But because we pack multiple meshes into the same light map atlas, we end up needing to do the traditional offset scale. And you might notice I said scale, not offset. Where is it? Small tangent. I hope everybody's aware that TRSs have this normal format. You have the translation on the end, and we have the rotation scale on the top, and we have a row of almost zeros. Not anymore. Offset gets jammed right there, and we save a few floats over there, so data gets a little bit tighter, packed faster. It gets easier to upload to the GPU. So we can say we have a matryoshka of data, and these all get fed into the runtime to our brand new component, that is the blink drawer. The blink drawer behaves similarly to your mesh renderers, where they attach to our blink drawing loop, very similar to the Unity itself. We even use the Unity update loop API. Again, there is documentation links on the slide notes. So this thing means that we did need to try to find the exact point into the pipeline where to call rendering, because it does need to interact with physics, with animations. We did have some hiccups. We're getting there. Like 99% of the cases works beautiful. And as I said, so it goes every frame, goes through every single active blink drawer, checks for its visibility. This is where the bounds of the collection is useful. So we can understand by using the curling group API if the blink drawer itself is within view. Not being within view, it gets skipped. But if it is, we send a call to the blink drawing bucket. This will be pretty much just a collection of compute buffer, meshes, materials, of all the information needed to issue draw mesh instance graphics commands. This is where I was saying before, we might not always want the blink drawing. The reason being, we do need to have 2 different buffers. We need to have the meshes themselves, and we need to have all the compute buffers about their positions, materials, and everything. So if we have a mesh that has a lot of bling and is moving very fast or pretty much every frame, we would need to be uploading both of those buffers into the GPU, which can reduce bandwidth. So in some cases, we end up being better just spending the extra memory on just baking all the bling into the geometry. But especially if they are more static, we rather go for the bling drawer, which does allow us more resolution to line maps, better performance, and less memory. Again, I have the code, I have the bling drawing loop, it does have just some groundwork, have the main methods of the bling drawing, I have the bucket itself. I didn't go to the shader, it's your traditional just instance shader. Results, that's what we want to see, numbers. So same mesh as before, after the visibility culling, 452,000 down to a little bit less than 400. Okay, 15% reduction, seems alright, seems good. More than the geometry itself and memory, light map resolution. These massively improve the rendering and visual quality that I cannot show none of you right now. It will be released, trust me, it looks delish. Okay, those are some of the more interesting and engaging features, and the AMP works. It's a great tool, it does everything, but it's slow. It can be very, very slow. It really, really feels really like Sonic when the thing that we need is to be at Sonic fast speeds. So let's try to understand what is the reason for that. If you guys do not mind, just a quick brief here. Okay, so first steps. This mesh already much better when we started at 600 megs, but can we be better than that? Evaluating our project, we understood that we don't always need this much precision on everything. So what we did was actually compress all the data. So some cases from float 32 to 16, sometimes even further than that, go all the way to a sine normal 8 bits. And this can definitely have a upwards to 50% less memory. So now the switch is definitely breaking better. But how do we do it, right? The main thing we did, the first thing we did was just compress on the CPU. Straightforward. We get all the data from the mesh. We have position, normal, UV0, all the way to 3. We have the color, etc. And then we just read them all and jam it into a new struct array of high complex vertex data. So this effectively is just a struct that has the map layout, and we do one after the other, after the other, after the other. Yes, guys, this is slow. Very, very slow. But guess what? It's repetitive, done over and over, on a very well-defined memory constraint. Compute shaders are here to save the day. So we're going to migrate all this code into compute shaders. First approach, direct. So we just do the exact same code, done on the compute shaders, just use the parallelism. Works great. So by issuing that call, everything's nice. I pushed it, everybody was happy, it was much faster. A couple of days later, somebody approached me and said, hey, we now need to compress a mesh that is not actually coming from the AMP. I'm like, sure, I'm gonna run the same thing, except it did not work because it had no normals. So now the high complex vertex data doesn't work because it would output normals. Sure, high complex vertex data, no normals. Great, shipped. Next day, no colors. Okay, high complex vertex data, no colors. Sometimes it would have UV1 have only two channels instead of 4 channels. Okay, it got boring very fast. So I was looking at it, and then I realized, am I just like moving bytes here and there? And isn't a mesh just actually bytes? Like just a huge byte soup? So let's change this. We start with our model, and we extract out of it the vertex data. Unity just provides this method to us. We can effectively just extract all the binary representation of the mesh as just a uint array. Can also extract all the mesh layout, so which channels does it have, the size of them. With that, I can generate what I expect out of it. So it doesn't need colors, or it does need UV1 as just 2 channels. Send everything to the GPU, effectively getting at the end another uint array with just the compressed data, shove back into the mesh, and the mesh gets small. Conceptually easy. How does the GPU black box looks like? I'm going to use the simplest example, just because less graphs. We're going to start with just a vector for a float 32s. I effectively send that as a binary string to the GPU, which on its end can read each one as uints, because the GPU just behaves much better at the 4-byte packs. Read them all as uints, just call F32 to F16, which still outputs a uint, but it does compress from the 4 bytes into the 2 least significant bytes of the uint with the data, and the most significant 2 are just effectively undefined, which means I can shove another uint there, going down from the 4 uints to 2 uints. When I stream it out of the GPU, the CPU can just, expecting to read just float 16s, it works. So it just gets 2 bytes on one, 2 bytes on the other, 2 bytes on the other. I do have all the code, so this is the CPU compression. We still use it in some very specific cases. Sometimes we do explode the 65,000 threads that the GPU requires, and instead of me having to sort out, split it, CPU will handle it. For every other case, which is like 99% of our meshes, I do have the calls for the meshes. I do have all the different compute shaders. At the very end, I am showing how we do all the different types of compressions. Most of them are very straightforward, except sign normalized vectors. Oh, guys, it's the worst, okay? You try to do it, it seems to work, everything's fine, and then sometimes the lighting guy will do it and the normal seems slightly off and they're gonna complain. Lighting guys complain about everything. But they're right, okay? They were right, I did have to find it just a bit and the end was off. Okay, same mesh as before. What is the difference, right? What is the impact? Just 900% faster, guys. It is so much faster. It reduced by 20, it made the entire pipeline 25% faster, effectively allowing us to, the reason for that is because the pipeline does much, much more. It doesn't need to read, the instruction file, it doesn't need to load all the data, bring all the meshes, combine everything, but this was a very big impact. Is it the end though? Not necessarily. As I've been talking all this time about compression, I'm not sure if everybody is aware, but different architectures treat binary as slightly different, or sometimes even the algorithms. In order for us to actually do the light map UVs, what we use is just XAtlas, which is very common and should be deterministic. That's what the documentation says, but guess what? Mac disagrees. So Mac people, whenever they would generate their XAtlas, they would be slightly different. What's the strategy here? We went for Cation serialization. So how does that actually work? We begin with our instruction file. Whenever we are importing that into Unity, we do all the generation that I talked before, generate the mesh inside the Unity library, but then we serialize that mesh into a cache file, and both the instruction and the cache get pushed into the repo, which means that every other team member gets to download it, and instead of doing the generation, they just deserialize the cache into the actual mesh into the library. This not only made it much more reliable, it also made it much faster, right? Because we don't need to spend the time generating, compressing, and everything. So it was great. Except sometimes, just sometimes, it would still not work. And we try to spend a lot of time debugging, a lot of time profiling. I even got to some stage that's slightly different issue. That is, it would just crash. After spending 20, 30 minutes going through the mesh, it would just crash. And what's going on? I started profiling, I started looking at it, and guess what's under the surface? JSON. JSON all the way to the bottom. We would just effectively get all the mesh, get all the data, all the numbers as JSON, put that as a string, put that into JSON, convert everything into bytes, write to disk, and back. We immediately would deserialize the mesh we just serialized just to be safe. Sounds great when you're doing a couple bytes, but when you're doing 6.5 million verts, it's not nice. Computers die. Okay, so what is the strategy here then? We're gonna actually go for a new mesh binary serializer. We start with our mesh. The serializer itself has just a byte array that is just effectively, that's it, a byte array that we're gonna do as the scratch. From the mesh, we extract all the different parts of it. So we have the name as a string, we have the layout, we have the size, bounds, triangles. All of that we can actually split into a few different data types. First of them is just value. Effectively, as a good example, is the bounds. You can think of it as just 2 vector trees, so just center extents. Each vector tree just 3 floats. So 4 bytes times 2 times 3, we end up with 24 bytes of raw data. we can just grab that raw data, push directly into the scratch, move the pointer forward. Another type is array. So we do have the triangles that we need to serialize, and that being an array, easy, we have the length, which guess what? Is just a value. We just can get those 4 bytes of the array of the length integer shoved directly into the scratch. For the values, we could do the naive approach of effectively just serializing each one of those values themselves. But guess what? Being an integer, it is a struct, which means it's memory aligned. We can just get the pointer for the first element and just loop through them all and push directly into the scratch, making the process faster. As you guys can see though, I did put raw data as a different data type because there is another part of the mesh that is the mesh vert data. We use it already on the compression going for the compute shader. We can just get the exact same data and shove directly into the scratch. Effectively at the end, we can just push that into the cache, which means a much faster process. I have the code, as always. Again, just a friendly reminder, you all can download this, can all read this properly, can all zoom in. I truly believe it will be readable once you zoom in. If it doesn't, find me at the coffee cart. Okay, so impact, right? Numbers. How much impact did this have? 50% faster writing and 65% faster read, which is the thing that most of our team was doing. Effectively, again, another 25% faster amp. We pretty much remove all the crashes. We haven't seen that specific type of crash again. We did see others, but we also allowed us to be safer against the different platforms. And the reason for that different platform mismatch, for those that are curious, Macs, when they're getting the string out of floating points, they actually have different representation. They round differently, which means our Windows computers were serializing the floating points slightly different and getting cache mismatches. So, okay, this is definitely been a journey. Had to do compute shaders, we have to profile a lot, and you might be wondering, why should we care all about this, right? It's just an editor tool. It's just something that we run, not every day, not all the time, not in a build. So why? Because at the end of the day, it's our team. At the end of the day, it's our team that is spending this time. People that are wasting 20 minutes at a time, 30 minutes. If it crashes, it's another 30 minutes and they had no feedback. So this is not only a productivity matter, it's also sanity. It's mental health. It's very demoralizing to just spend your entire day looking at load bars. And you might be wondering though, like, how did I identify this problem, right? Did I use this tool every day? Did I use it all the time? No, okay? I almost never use it. I would only use it to validate some PRs, test some random ideas, how big would something get, how much can we compress something. So what was the strategy here, right? How could I find all these answers? First part is ask questions. Go after your team members. Ask them not only how fast something's going to take, but how is their work? How is their day? How things are going? Are they having a good time? Are they having a bad time? What could be different? Because the thing is, we in game dev have this very, weird ingrained feeling that we're going to find our way. We're going to work around the problems. We're going to hack the heck out of it. But sometimes we should just fix it. Sometimes we should just improve the functionality, right? And the thing is, by asking people questions, they will come after you. They will send you an 8 p.m. message. Victor, have no clue when you zoom this fast and when you scroll this bar, the whole amp stops working. That's okay. That's okay. Have been there a couple of times, had to find some very random bugs. But it's important to be there and listen to your team. It's important to listen to those problems. Exactly what's triggering them, what's taking their time. And even if you're not going to do it right then and there, being there to listen to things allow you to collate different feedbacks and understand what is the actual pain points. The reason being, sometimes, as every programmer, we love to just go to solutions. We like to just write that code, and it's not always what the people need. So it's really important for us to be paying attention, getting all these different points of view, understanding the exact thing. And did I need to do it all myself? Did I need to find with all the solutions? Obviously, no. The same way that this is work that is being done for the team, we need to rely on the team. So by listening to them, even if it's a more artist people, not so tech oriented, they will come with solutions that sometimes might not exactly be how it works, but it's in the way. Because they're gonna come and say, oh, I don't know, if you grab the mesh, you could just, just rotate it. Like, it's bytes. It's not, you don't rotate bytes. But you get the idea, right? It works. In some cases, some of our team members will actually be more tech oriented and they will be more engaged once they actually write their code. Once they actually go there, do the sausage themselves, they will be more passionate about it. Not only that, you're not gonna have to do every single Jira ticket, which makes you a little bit happier. I was happier. So, okay, folks, I just talked for a long time, non-stop, and what the heck happened here, right? What I would like you guys to leave this room remembering. First of all, profile frequently. Everybody that works with me knows I complain this all the time. We should all profile. Profile the runtime, but also profile the editor. If you're penning around the scene and it's a little bit stuttery, it shouldn't be, because it runs at the build. Profile your editor. You press a button, it took a few seconds. Profile the button. It's also important to be always profiling. Whenever it's filled, it will take you like 10 seconds, guys, so just profile. I like the profile, but that's a whole new discussion that it's a coffee cart line discussion. Besides that, assets are just byte soups. We love to think of our text files and models and whatever that might be as like this nice, packed, complex thing. At the end of the day, computers are just bytes. Everything is just bytes. So effectively, by understanding the byte layout, we can actually do all these different forms of compression, reading, writing, to make processes faster. But another point is GPU are not only there to draw your frames. You can use the compute shaders, which everybody has on their minds. They do their magic. But guess what? You can use actually the GPU to render data. We can render the integers, we can render index, we can actually read from them as well. So these allow us to actually do some nice transformations. Last, talk to your team. Game development is, for most people, is not an individual task. It's not something that we sit on a corner and 5 years later we have a game. Most of the time, this is something we do with people. So we need to be respectful of their time, we need to be there for them, we need to be enabling them to do their best, because that's the reason why we are together. And that's my talk. So, thank you very much. Questions? Yes, I was told you have to come here. If anybody doesn't feel comfortable, come in here, raise your hand, I will repeat your question, and I will butcher your words, so be prepared. But
hi, thanks for the talk. I was wondering, to the extent possible, you could maybe give us a little bit of larger context of why the project is using these atomic meshes and sort of what overall purpose in the larger picture that serves.
I really cannot, but not leave you just hanging. I'm gonna go back to one of my previous projects. When I worked in VR, it was an open world game, and we had, at the very beginning, just 2 artists making an open world game. For that thing, we ended up in a very similar solution where they designed just a couple of different assets. And whenever they're just laying on the level, you can imagine the same rock, in order for it to look different, you need to put like 10 or 20 of it, one next to another, right? So we end up with a lot of geometry going inside of them, going under the ground. So we end up with a very similar situation where we would just go through, do the visibility calculations, and be processing every mesh. And after that, we would also generate reserialize everything into prefabs. Was nowhere near as this elegant, but is definitely a usage of it.
Cool, thank you.
You're welcome. Other questions?
I might just take next.
Yep.
Yeah, I love the idea of using compute shaders to speed up like dev workflows and artist workflows. But I was wondering, are these just things that run on with the developers' workstations, or do you also need to fit out your build farm with GPUs in the machines?
So the question is if whenever using the compute shaders, if we had to organize the build farm to actually has GPUs, or we would be running on people's computers. In our specific case, we were able to actually use everybody's computers, because whenever somebody is importing something, they do need to do a lot of manual setup. So sometimes we would enable the blink drawer, or we would need to change the visibility, or in some cases even split the meshes, because if we need something to spin inside of a total, it needs to be split off into an individual model so it can be animated. So because somebody's already doing, we might as well just run on that personal machine. We started discussing, especially for light map evaluation, to improve our build machines to actually include GPUs. But in the end, we ended up with just doing everything on people's machines. Anybody else? I'm going to take that as a no. So, muito obrigado for everybody that attended. That is the link. I did put my LinkedIn. So I don't know. I'm very bad at reading everybody's messages on different platforms, and LinkedIn I end up reading a little bit more often. I don't know if you want to message me, or as I said a couple times, coffee cart. Easy to find me. There's coffee or there's desserts. I'm there. Thank you, everybody. Not so bad.